In this presentation, I want to discuss inference in educational, behavioral, and social research from a very pragmatic perspective. We often conduct our inferences thinking about the theory behind those inferences without relating that theory to what actually happens in practice. One of the best descriptions of inference that I have read comes from an article that was published in 1995 in the Journal of Educational and Behavioral Statistics. That particular article was focusing on hierarchical modeling in the social sciences. However, I believe that Draper's description of inference goes beyond any particular method of analysis and is really a valuable way of thinking about inference in any study that we do in the social and behavioral disciplines. What he did in this study was he looked through many research articles and tried to find examples of how data were collected, how individuals were assigned to conditions, and what kinds of inferences were made as a result of this. And based upon that, he came up with 4 possibilities. From those 4 possibilities, he named 4 different types of inference. They're good names, I want to use them, and I want to discuss them right now. These 4 types of inference are calibration inference, sampling inference, specific causal inference, and general causal inference. To understand these, you should start with thinking about my previous presentation about 2 general types of inferences that we make. One to the population of units that we are sampling from, and one to the population of all possible randomizations that we could do in an experiment. The first type of inference I refer to as population inference. The second type I refer to as causal inference. That is, we want to make inferences back to the population that is represented by our sample, or we want to infer causation from our single randomization, or we might want both. And those 2 general types of inference lead to these 4 more specific types of inference that Draper identifies. Let's start with calibration inference. In calibration inference, the way the study is conducted is that there is uncertain exchangeability of samples. Now, I should take a moment to explain what I mean by uncertain exchangeability, or UE, of samples. You often heard it said that we randomly sample from the population of interest. The fact is we never actually randomly sample from the population of interest. Even when we take a random sample, that random sample isn't from our complete population of inference. It's rather from an accessible population from which we were allowed to draw a sample. So rather than thinking of this in terms of random sampling, think in terms of what we hope to achieve with random sampling. What do you hope to achieve when you take a random sample from some accessible population? You're hoping that you end up with a sample that represents the population with regard to any variable that is related to the response measure. So in essence, we can think of that this way. Do I have a sample in which I really could change out people from the sample and the population and still have the same characteristics in my sample? That's what we mean by exchangeability. So when we have uncertain exchangeability, that means replacing the sample of individuals in my study by other people or other units from the target population may leave me with a sample that's very different from the one I have, meaning that you cannot think of just moving people back and forth from your population and your sample will leave you with the same kind of sample because your sample doesn't adequately represent the population. This is most often the case when we have samples of convenience or convenience samples. That is, when we're using individuals in the study not because we did any kind of random sampling at all, but rather we're using intact groups of individuals that are available to us. It's convenient for us to look at these individuals. So we know from my previous discussions of population inferences that if we're using this convenient sample, and now more specifically using this exchangeability idea, we're using a sample in which the individuals in the sample are unique with relation to our population of interest. That is, we can't just trade back and forth people in our sample with those in the population and expect that our sample is generally going to be about the same because we took a convenience sample. It has unique characteristics. So therefore, we're not going to be able to make those population inferences. Furthermore, with respect to causal inference, there is no assignment to treatment. This would be the case if we're using an observational design in which we have intact groups that we're comparing. For example, if we go into a school and look at classes that are teaching algebra and we compare instructors who are using manipulatives and instructors who are not using manipulatives and measure the algebra achievement of the students in those classrooms, but those instructors were already doing that before we ever got into the school. That is, we were not responsible for assigning them to conditions. We're just looking at what already exists. There is no random assignment of students to the manipulatives and the non-manipulatives conditions. So here we have not only a convenient sample, but we have a convenient sample that has been broken into two groups through means that are outside of the control of the researcher. So therefore, not only is population inference a problem, so is the inference for causal reasons. So therefore, it might seem like you can't do any kind of inference at all. Relating this to the concept of validity in this chapter, we have low evidence of external validation and we have low evidence of internal validation. That is, we cannot generalize to the population. That has to do with external evidences of validity. And we cannot infer cause. That has to do with internal evidences of validity. External evidences of validity are about, can we take what happens in our study and expect that to happen outside our study? Internal evidences of validity has to do with, can we claim that there is actually cause and effect? And when we have uncertain exchangeability, i.e. convenience samples, when we have an observational design, that is, no randomization to conditions, we can't do either. So maybe we can't make inferences. Draper suggests that we should still look at our inferential results, but refer to it as calibration inference. That is, when we look at our p-values and our confidence intervals, these are not giving us anything about population parameters or about cause and effect size. But nonetheless, they are curbing our enthusiasm. Here's the quote from Draper. People are quite good at identifying interesting patterns in data. So good, in fact, that they're capable of finding them even when they are not really there to be found. We need some form of calibration inference to restrain our enthusiasm in the search for scientific relationships. And this is true. When we look at a set of data, it's real easy for us to detect patterns that are just happening due to chance, even when we don't have random sampling and even when we don't have random assignment. We can detect these patterns. So what our inferential values, like our p-values and our confidence intervals, do for us is they take into account the variability among our units that include the potential for patterns to arise just by chance and not due to anything else. So this does help curb our enthusiasm about our results when we use inferential methods rather than just simply looking at a pattern and saying, we found something. If our inferences tell us, well, we're not so sure that what we're seeing isn't something that is just a chance finding, then we're not going to be so prone to focus so much on description when talking about either causation or the population. You'll see here it says example Chicago study. I'm not going to talk about those specific studies, but these are examples that are used in the article in which he talks about the idea of having both a convenience sample and an observational design. So he provided an example in the article from a study that was done in Chicago. The next kind of inference he refers to is specific causal inference. In this, you have uncertain exchangeability of your sample with population values. So, for example, you have convenience samples. But this time you did something to control potential confounding factors. Of course, the strongest method of control, the gold standard in experimentation, is random assignment. But Draper doesn't want us to just think about random assignment. He wants us to think about the reason we do random assignment. It's to control potential confounding factors. And so what he says here is if we have allocated to our conditions in such a way that we can really ignore the allocation mechanism and assume that we've arrived at two conditions that remove confounding factors, then we can consider this as a control of those confounding factors. So for example, if you have matching and you match on all the extraneous variables that are strongly related to the response variable, you don't really need random assignment. The problem, of course, is often when we do that matching, there are additional extraneous variables that we can't think of. But still, Draper makes a good point. Just like he doesn't talk about do you have random samples, he talks rather about do you have a sample that's just like the population. Similarly here, rather than saying did you use randomization, he's saying did you control all the potential confounding factors? If so, we have low evidence of external validity because we do not have samples that are necessarily representative of our population, but we can ascertain that there is a cause and effect relationship when we see that relationship. We can, in fact, infer that it was the condition the individuals were in that led to the responses that they provide. So we do see cause and effect. Here's a quote to explain this a little more. In permutation inference, you condition on the observed data and consider all possible ways in which the observations might be rearranged. A p-value may then be calculated by asking how often differences as large as the one observed or larger would occur. That is, you're using the p-value as an estimation of what you would get from a randomization test. This is one of the main points that was made in Chapter 1 that is now carrying forward to Chapter 2 because it has to do with the type of inference we make. In this case, specific causal inference. Then there's sampling inference, when we do have a sample that's representative of the target population. But let's say we still have an observational design. That is, we're comparing conditions that already exist rather than randomizing to conditions or using some other method for controlling confounding variables. If we have a representative sample, but in that representative sample we're now comparing individuals that are in existing groups, then we can, based upon our inferences, infer to the population, what I've called population inference, but we cannot do what I've called causal inference. So we have high evidence of external validation, being able to take the results from our sample, apply them to the population, but any differences we see in our conditions we cannot attribute to the conditions themselves. That is, we have low evidence of cause and effect, or low internal evidence of validity. In hypothetical sampling inference, the data values or sets of values before us are interpreted as a random sample from a hypothetical infinite population of such values as may have arisen in the same circumstances. The distribution of this population will be capable of some kind of mathematical specification involving a certain number, usually few, of parameters. And that quote is back in 1925 from Fisher, who even then went beyond the idea of random sampling to saying, basically, can you interpret your sample as having been chosen at random? Finally, we can put this all together. What if we have a representative sample, and what if we're controlling the potential confounding variables? The easiest way to envision doing this is through a random sample from our population and through randomization to our conditions. In this case, we have both high external and internal evidence of research validity. And so you can both infer that you have cause and effect and infer you would have that in the population as well. Interestingly enough, notice the example that Draper used in his article. He said none found in the literature that he reviewed in order to try to come up with examples to exemplify these different types of inference. I'm not surprised by that. Seldom is it the case that a study is done in which there is a random sample and then randomization. So don't feel bad when you're unable to do both, even though you learn that that was a great thing to do in your statistics courses. It's seldom done because it's very seldom that we have the opportunity to do that, to both take from our target population or even our accessible population a random sample and then have complete control over what we do with that sample. In specific causal inference, there is something causal going on for the people in the experiment. In general causal inference, there is something causal going on for everybody in the target population. Here's a little diagram to put this together. In the rows, we're looking at, can we justify the exchangeability of sampled and unsampled units in the target population? That is, can you take units in your sample and randomly exchange them with those in the target population and basically have the same kind of representative sample? That's what we mean when we talk about a sample that's representative of the population. In the columns, can we look at our conditions as though that we had created those through randomization to those conditions? Which in essence means, have you had strong control over confounding variables? And now you see all the possibilities. When it's difficult to justify that your sample represents the population, then you either have calibration inference, because it's also difficult to justify the ignorability of assignment to treatment conditions, or you can have causal inference, but that causal inference is for the sample you're working with, not the population. If you can justify that your sample is representative of the target population, but you did not have randomization to conditions or otherwise you did not control the potential confounding variables, such as when you're doing an observational study, then you have sampling inference. We can infer our results back to the population, but we can't infer cause and effect. When you can do both of those things, justify that your sample is representative of the population, justify that your conditions are the same as if you had randomized to conditions, and maybe you even did randomize to conditions, then we can have general causal inference. So in your meta view, I want you to consider the idea of population inference and causal inference. And what we're doing here is looking at all the possible combinations of whether or not we have either of those two types of inference, which leads us then to 4 specific types of inferences that we can make. Also recognize that what this tells us is, even though in an experimental design course we talk about doing experiments which focuses on causal inference, that even if we extend to observational studies what we learn in this course, we can still do inferences, but it's inferences of a different kind, and we have to rein in our enthusiasm for our results when we have less ability to make either a causal inference or a sampling inference.